is and derivatives is velocity, because like we've seen before, velocity and position are connected, and acceleration as well, through derivatives. So like I talked about, since derivatives is just a slope, if you have a position graph, so if you have a position graph given to you where you have the x and the y-axis, and down here it's meters, and here, or sorry, it wouldn't be meters. Down here it would be seconds, and up here it would be meters. Okay, then the slope of your position, because the derivative is always the slope, would be delta y over delta x, which in this case would be meters per second. So what that means is that the derivative of position is velocity. And similarly, the derivative of velocity is acceleration. So we have a way to do that now. So here it says the position of an object at any time t in hours is given by 2t cubed minus 21t squared plus 60t minus 10. Determine when the object is moving to the right and when the object is moving to the left. So if an object is moving to the right, what can we say about the velocity? Does anyone know? Anyone taking physics? Huh? It's positive. So as something's moving to the right, that means that its velocity is positive. And if something's moving to the left, it means that its velocity is negative. That's, Sebastian, that's for when you take that Physics 20 exam. Keep that in mind. Okay, that's some important facts. So if we want to do that, what we need to figure out first is the velocity. So if we have position, it's pretty easy to find velocity. I just find s prime. So s prime of t is equal to v of t, which here would be equal to 6t squared minus 42t plus 60. Okay, now, if I want to figure out when this is positive, when this is negative, without graphing it, which would be something you could do if you had a calculator, but let's imagine you didn't. How would I do it? How could I figure out when this is going to be positive and when this is going to be negative? Find the zeros. Pretty much a lot of the time in these questions, you're going to end up finding the zeros. So I would be setting this equal to 0, 6t squared minus 42t plus 60, and set it equal to 0. And solve that. Now, these numbers are pretty high, so the first thing I would definitely do is divide everything by 6. So I get t squared minus 7t plus 10, which makes it much easier to work with. Cyrus, you have a question? Or are you just stretching? Okay. So that is t minus 5 and t minus 2 for factoring. And so my two zeros are 2 and 5. Which means this graph crosses the x-axis at 2 and 5. Now, at that point, you can do it a couple different ways, up to you kind of how you want to work with it. Personally, what I would usually do is make a little number line, where I put 2 and 5, because if those are the zeros, right, like a parabola, and you could just think about this parabola if you wanted to, I guess, and you could do it that way. This parabola is positive, so when it's 2 and 5, it's because it's going to look like this, right? Where it goes through 2 and 5. So it's going to be positive over here and positive over here and negative down below. Okay? We're looking at where it's above and below the x-axis. Okay? However, you could also just use these values to test. Like what I would probably do is I'm like, okay, I know 2 is going to give you a 0, so I'm just going to pick any number under 2. Okay? A number under 2 is 0. Because if it's not a graph that you know what it looks like in this case I know what the graph looks like. But if I didn't know what the graph looks like, this works. So I just pick some number less than 2, like 0. If I plugged 0 into this expression, for t, what would I get? 60. So that's positive, so I just put a little plus sign there to represent that in that section it's positive. Okay, then I pick another number that's somewhere between 2 and 5. So 3, maybe, or 4. There's lots of choices that would all work. And I just think about this, and I don't necessarily need to get the actual answer, but I think about what would it be if I plugged 3 in for t. If I did 6 times 3 squared minus 42 times 3 plus 60. Or you could use this expression down here. It's easier, right? 3 squared minus 7 times 3 plus 10. And I just think about if it's positive or negative. So that one's a lot easier to look at, because that would just be 9 minus 21, which is negative 12, plus 10 is negative, so it's a negative number. And it's a parabola, so I kind of know what's going to happen. But, you know, you could also test a value. If I plug in like 6 into that expression, and I do 6 squared is 36, minus 7 times 6, which is 42, so that's negative 6, plus 10 would end up being positive. Okay, but what I can see, once you get that, it tells you where it's positive and where it's negative. And that tells you where it's moving to the right and moving to the left. So it's moving right from, and you could do it in different ways, but it's from negative infinity to 2 and 2, or sorry, not 2, 5 to infinity, and left from 2 to 5. Okay, technically, it doesn't really matter about the endpoints. Like, you'll notice I use soft brackets. I've heard that they accept square brackets in these kind of answers, but to me, at the value of 2, what's the particle doing if it was moving to the left or the right? Like, at the value of 2, what direction is it moving? It's not moving at all. It has a velocity of 0 at that point. So to me, it doesn't have a direction, so you shouldn't include the endpoints. But I've read that some problems, or some books and stuff, include the endpoints. So if you did, I wouldn't mark it wrong. Does this make sense to everybody, though? Here, he's moving right when the velocity is positive. He's moving left when the velocity is negative. We're going to be doing a lot of stuff like this, looking to figure it out, because this also tells you about the original graph. You know, the graph of the position would be increasing from negative infinity to 2, then it would be decreasing from 2 to 5, and it would be increasing again after 5. So what that means is it helps me draw, if I wanted to draw my curve, my S curve, like the position curve, I could, because I know what's going to happen at 2 and at 5. I don't know where, like I don't know exactly where on the axis and stuff it's going to be, but I know that I'm going up, 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 and at 2 I start to go down, and then at 5 I start to go up again. Okay, I know that that's going to happen because it says it's increasing less than 2, decreasing between, and increasing again afterwards. So I know that that's what my position looks like. Okay, I know that the maximum happens at 2, the local max happens at 2, and the local minimum happens at 5. I can see that from this information. Okay, so it gives you a lot of important information. What we're going to be learning, the big thing that we're going to be learning, here, this is horizontal. This is the same concept. Something has a horizontal tangent when the slope is what? If it has a horizontal tangent line, what's the slope of the tangent line? 0. So here we're really looking at where this would have zeros. I think they do it in your notes just using graphs. I think they're there. But really, like what you would do is you'd find y prime, and it's 4x cubed minus 4x. Which factors? So that's x, 4x would even be better, times x squared minus 1, which is 4x times x plus 1, x minus 1. So I know that the derivative graph has zeros at what values? One and negative 1, and what else? Not 4. So 1 and negative 1, Haley got them from here. This is 1. This is negative 1. What would this be? 0. Okay, because 4 times 0 is 0. That's why. If we plug 0 into that, it would give us a 0. So there's 3 zeros rather, positive and negative 1, and at 0. So those are the places where it would have horizontal tangent lines. Okay, it's that easy. If you look at the picture that's in your notes, I believe, is there a picture of a graph there? No? Oh, okay. Well, if you look at the graph, there could be a picture of a graph. And if there was, you would see that the original graph, y, I'll do y in black, would look something like this. That would be the original graph. And so your derivative graph would have zeros at the maximum and minimum. So it would look something like that. Okay, the derivative graph. Okay, so you'd see that the zeros are where the max and min of the other graph are. That's how it works. Okay, so anytime there's a horizontal tangent line, like at the minimum there, you would have a 0 on the derivative. Okay, that's how it works. Oh, here it is. Isn't this the thing? Oh, it's on the next slide. Do you have it?
Yeah.
Okay, cool. And mine looked basically exactly like this, so you can look at this if you want. It's not as good as the hand-drawn one I just did. But you can see the same thing. So there's a minimum value right here. So there's a 0 underneath. And like we talked about the other day, the fact that this 0 goes from negative on this side to positive on this side tells me it's going to be a minimum. Because negative to positive means it's going from decreasing to increasing, which causes a minimum. Okay, is that kind of starting to make more sense? I'm hoping that that starts to sink in. Then if I see here, when I'm looking at a derivative, this is really what I do. I just look at all the zeros, and I just mark, is it positive or negative? So here, between these ones, it's negative. Over here, it's positive. So from positive to negative means up, then down. It means a maximum, so this is a maximum. And from negative to positive, like at the end there, that's down then up, so that's a minimum. And I can see that there. That's how I interpret these graphs when I'm doing them. Okay, so we're getting into what we'll call, well, not just we, everyone in the world will call product law. Okay, so given two functions, x cubed is f and x to the power of 6 is g. If we are given a function h of x is equal to f times g, which is x to the power of 3 times x to the power of 6, everybody understands that x to the power of 3 times x to the power of 6 is x to the power of 9, right? Everyone's with me on that? Okay, so that's what h is. H is x to the power of 9. So h prime then would be what? 9x to the power of 8. Okay, now, since we know that h is just f times g, which is x cubed times x6, would it work to take the two derivatives and multiply them together? Let's try it. So if I took the derivative of x cubed, what would that be? 3x squared. And the derivative of x to the power of 6? 6x to the power of 5. And if I just multiplied those together, will I get the right answer? That'll be 3 times 6 is 18. X to the power of 7. Is that correct? No. So that doesn't work. Okay, and that's really what I'm trying to show you here is that when you're multiplying, when you have the multiplication of two things, you can't just take the derivative of both of them and multiply them together if you're trying to find the derivative. It doesn't work. Okay? There is a rule that does work, but that very clearly does not work. Okay? Everyone agrees with me? So there is a rule. It's a pretty straightforward rule, I think. We'll see. We'll see if you agree with me or not. But I think it's fairly straightforward. So the rule is, and I'll write it down here and then we'll try it with this very simple one, because simple ones are nice. Okay, the rule is that if you have the multiplication of two things and you're trying to take the derivative, so if I'm taking the derivative of f of x times g of x, what I do is I take the derivative of f and I times it by g, so g, not g prime, then I add that to f by itself times g prime. Okay? So in this case, I would never do it this way for this question, because this question, it would be easier to just get x to the power of 9. But let's imagine that we were trying to do it that way. So if I know that it's x cubed times x to the power of 6, and it's the derivative of that I'm trying to find, what I do is first I take the derivative of f. So this first function is f. So I take the derivative of that, and I get 3x squared. Then I just take g, and g is just x to the power of 6. There's no derivative, so I just take x to the power of 6. Then I add that to just f, which is x cubed, and I times it by g prime, which is 6x to the power of 5. Then I simplify that, so that's 3x to the power of 8 plus 6x to the power of 8, which is shockingly 9x to the power of 8. Okay, so like I said, on a question like this, you would never do this. You would just multiply it out, x cubed times x to the power of 6, and get the answer, and then take the derivative. That would be easier. But in a lot of questions you're going to be given, the multiplication would be very difficult, if not even impossible. Okay, so you need to learn the product rule for those cases. Okay, so for cases where you wouldn't ever want to have to multiply. So we're going to look at a few right away, but it's a pretty straightforward rule once you try it a few times. I know it probably looks confusing at first, but it's not too hard. Okay, so let's look at this one. So here's the rule written down. Okay, so f times, and it's written a little bit differently, but it's the same rule. So fg prime, so f times g prime, the derivative of f times g, is fg prime plus f prime g. That's out of order. I usually do it the other way, but I'm sure that was just how it was written in the book. Okay, but it doesn't matter what order they go in, right? Because you're just adding up two things. So personally, I always do f prime first, but it really doesn't matter. So let's look at this one. So this is one where you could multiply through. Like, you could always technically multiply through. Okay, I could, if I wanted to, multiply this times this, and then get an answer, and then do the derivative. Okay, you could do that. You would get the same answer. However, it's not super pretty, so maybe I don't want to do that. Instead, I can just take the derivative of the two things. Now, I would definitely write this down as x to the power of 2/3 times 2x minus x squared, okay, instead of leaving it as a radical. So all the time when you have radicals, you should write them instead as a fraction exponent. Okay, so it's 2/3 there. So if I'm doing the rule, so I'm just going to write down the rule. I always write it down. It's f prime g plus g prime f for f g prime. It doesn't really matter. Like, the order of these things really doesn't matter. So I take the derivative of the first term. It's the first thing. So x to the power of 2/3. What's the derivative of x to the 2/3?
2/3 x to the power of negative 1/3.
Perfect. Okay, so it's 2/3 because the 2/3 comes down, becomes the front number. Then we subtract 1 from 2/3. So if I subtract 1 from 2/3, I get negative 1/3. And that's times g. So g is just what's in the brackets, so I just times it by 2x minus x squared. And I have what's in the brackets. Then I go plus, and now it's g prime that I use. Or you can write f first, it really doesn't matter. Okay, but if I'm taking g prime, the derivative of what's in the brackets there would be 2x is 2. And what's the derivative of negative x squared?
2x, or negative 2x.
Negative 2x. So it's going to be 2 minus 2x times f, which is just x to the 2/3. Okay, now this is a part that people won't like, but that you have to do it correctly. You need to factor things at this point. Okay, so this is why in the pre-calculus unit we spent time factoring, and we spent time factoring things with fractions in the exponents, with negatives in the exponents, and it's for this moment. It's come to pass, the time that you actually have to do that. So you need to be factoring here. So what you look for is you look for common factors. So here, the common factor would be the x's, and you will pull out the lowest exponent. So what's the lowest exponent for those two x's? Negative a third. So I'm going to pull out x to the power of negative 1/3. Okay. Now you should also always factor out, if you have any fractions like I do here, 2/3, you should factor out a third. You should factor out the denominator. So I should pull out a third. Okay. So left over, I have to think about it. I have to think, okay, what do I need to multiply 1/3 by to get 2/3? It's not a trick. 2. So it's going to be a 2. X to the negative third is already here. Okay, it's right there, so I don't need it again. And I have to multiply that by this part because it's not there and I want it to be. Okay? Now for the next term, I have x to the 2/3. I want x to the 2/3, and I have negative 1/3. So what will I have to multiply x to the negative 1/3 by to get x to the 2/3? No. What did you say, Haley?
Nothing.
Are you sure?
Yeah.
Okay, so remember that when you're multiplying powers, you add up the exponents. So you need to think about what exponent would I need on x to add up to 2/3. So if I'm at negative 1/3, what will I have to add to it to get 2/3? 1 whole. So it's a 1 there, and the 2 minus 2x is also there. Now, hopefully what you see here is what's important is that what's in the brackets is now very easy to work with. That's the point of doing this, is it makes what's in the brackets extremely easy to work with. I can just multiply this out and this out, and I get 4x minus 2x squared plus 2x minus 2x squared. Okay. Now the stuff that's out front, I have a third. Instead of writing it as a third, I can divide this all by 3. And instead of having x to the negative a third, I can make it positive 1/3 and put it in the denominator. Okay, and that is how it should look. Okay, now we should simplify the top part. So we end up with negative 4x squared plus 6x over 3x to the 1/3. Now there is something more you could do if you wanted, if you realized that you could do it. Here, the top, what could factor out of the top there? 2x, so I could do that. If I pull out a 2x, or even negative 2x, I don't know, I get 2x plus minus 3. Now I have an x here and an x here. I could combine them. That was x to the power of 1. So what I can do is I can get rid of x to the power of third on both the top and the bottom. So if I take away a third from the top, I get 2/3. And if I take it away on the bottom, I get 0. So it would end up looking like that. Honestly, though, I'd be quite happy if somebody got this. It's fine either way. I mean, it has just, both of them have a fraction exponent in them. But I'd be fine if somebody actually managed to get to this step. This is a good step. But realize that this would be considered fully simplified and would likely be what would be on your multiple choice. Okay, so you would have to recognize that this answer is the same as that answer.
So that equals the very first one you got?
Yeah. Okay, so it's quite a lot of steps to do that, obviously. And it's going to be very slow at first, so you need to do it. What I end up with is people are like, I'm not going to do that, I'm just not going to simplify it. And then on the test, they don't know how to do it, and they don't get any of the questions right, and it's terrible. So it'll be very slow at first doing it, but it always works out very nicely where things all cancel together and things kind of just work themselves out. Okay, so we are going to do another one. It'll be very fun. Okay. Does anyone have any questions about it? about a step. Did I mess up somewhere? Is it okay? Okay. If you do have questions while you're working on it, let me know. Okay, so I'm going to do this second one. I'll just do it over on the side here. This one it looks like it'll be easier because it doesn't have any radicals in it. Radicals make these questions harder. Like you end up with these fraction exponents, which is what makes things hard. So here if I'm doing it, I just always identify, remind myself this is f and this is g, okay, for my own benefit. Okay, so when I'm doing y prime, personally when I'm doing it, I don't really think that much about anything. I just am trying to remember to do it where I am going to have one of them the derivative of times the not derivative plus the other one's derivative times the not derivative. That's kind of what I'm thinking. So I do f prime, I get 4x plus 3. I do g, which is that whole thing, 3x squared minus 2x minus 2. Okay, plus, I'll just do it down here. Then I take g prime, which is 6x minus 2, and f, which is 2x squared plus 3x plus 7. Okay, now this is not very pretty. I would say you definitely need to expand it and simplify. There's no common factors, so you can't take anything out here. So you just need to do the painstaking work of expanding and simplifying it.
How do you know if there is, how do we know if we have
I look for common factors. So here, there's 4x plus 3, but then there's no 4x plus 3 in the other set. Okay, there's 3x squared minus 2x minus 2, but there's nothing in the second set like that. Okay, there's nothing, 6x minus 2, there's nothing there, so I'm kind of just out of luck. There's nothing in common. So if there's nothing in common, you're going to be looking at doing some expanding and simplifying. So we just expand it out. We do all our fun arrows. It's going to be a fair amount. Okay, so it's 12x cubed. I suggest kind of trying to cut corners a little bit personally. It's what I do is I always do one and then the next right away. Just so just a way of doing it a little faster if you haven't already picked it up is that I do 4 and 2 and 3 and 3 because I know they're both going to be x squared. Because 4 times 2 is going to be 8x squared and 3 times 3 is going to be 9x squared. So I look at that, I'm like, okay, it's 9 and negative 8. That makes positive x squared. And I just skip a little step by doing that. Then I do the next two the same way. I know it's going to be negative 8x and negative 6x together, which is negative 14x. And finally, the last part, I know it's 3 times negative 2 is negative 6. That's how I do it a little bit faster. If you're not someone who, if you already feel like expanding is hard enough as it is, then don't try to skip steps. But that's how I skip a little bit of steps. So I would do the first two, so 6x times 2x is 12x cubed. Okay, then I would do the next two. So I would do 6x times 3x is 18, minus 4 is 14. Then I would do the next two again, so 6x times 7 is 42, minus 6 is 36, minus 14. Okay, and then it does simplify quite nicely to 24x cubed plus 15x squared plus 22x minus 20. Okay, so it simplifies to just a cubic expression. What is the other way I could have done that problem? Not done it at all. Just skipped it.
Just take them white out.
The other way you could have done it is just, I mean, not if I asked you to do it by product law, but you could have done it just by expanding here and then taking the derivative of your answer.
Wow.
You would get the same thing.
I feel like I wasted time.
I mean, no, I think they take similar amounts of time. One isn't significantly shorter, I don't think. But it could be shorter. Now, the last one, let's just do it on a new slide here. I'm going to
Wait, so that's
x cubed. Yeah,
it?
yeah, that cubic, yeah.
Oh.
So it's 6x plus 5 times 3. This is one that if I wasn't told to do product law, personally, I probably wouldn't. I'd probably just multiply this out. You are going to get a worksheet where you're asked to do the product law, so you need to use it, like even if you feel like it would be easier to do it the other way. It's just practice, because eventually we're going to get to ones that there's no way to do it without the product law, like if there's trigonometry involved. Like if you have like x times sine x, there's no way to multiply x and sine x together to like get an answer. So you do need to know the product law. So anyway, though, this is one where I probably wouldn't if I didn't have to. But this is f, and this is g. So I do f prime, which would be what? 6. Times g, which is x cubed minus 3, plus g prime. What's g prime here? 3x squared times 6x plus 5. Okay? Pretty easy, actually. So maybe it would have been the right choice to do this, because this is a pretty easy expansion. They went from hard to easy. I don't know why they were ordered that way. It's fun, though. Okay? 6x cubed minus 18 plus 18x cubed plus 15x squared. So you end up with 24x cubed plus 15x squared minus 18. Okay, so if it's just going to be a simple polynomial expression, multiply it out and simplify it. If you have fraction exponents or negative exponents and things like that, you need to be factoring and simplifying. And that is going to be the challenge on this worksheet for sure, because I've seen a lot of people do this worksheet, and I know that that's what people have trouble with. So you probably will need a spare piece of paper to work on it. Clayton?
Would you factor that last answer?
If it was possible, like here you could pull out a 3 if you wanted to. You don't need to, though. Generally speaking, like, your answer doesn't have to be factored. You would want to be able to spot the factored version if it was given on a test or something. But this and this are both equally simple. So either way would be fine.
So, like, what is that? Like, what do we just learned?
That's the derivative
Okay.
of this function. So it's the tangent line,
Okay.
like the slope of the tangent line. If I plugged 1 into it, it would give me the slope of the tangent line at 1. Okay. So it's they're just way harder. If you have 3 or 4 things multiplying together, the rule continues. So like if you have 3 things, you do the derivative of the first times the other 2, plus the derivative of the second times the other 2, plus the derivative of the third times the other 2. You don't have to do that very often. Let's just do one example where we actually use this information for something. So find the slope of the tangent to the graph of the function f. So if I was doing f prime here, I would take the derivative of the first, so that would be 6x, and times it by the second, so 2x cubed minus 1, plus the derivative of the second, which is 6x squared, times 3x squared plus 2. And now it's up to you what you want to do, because you could simplify this out, or if you're given a situation like this where they give you a point, you really can just plug it in at this point. Like I know that this, the 1 value, is my x. So I could just plug it in right now if I wanted to. So f prime of 1 will be 6 times 2 minus 1 plus 6 times 3 plus 2. And please notice, because I see a lot of you guys, when you're plugging in numbers, if you're plugging in a 1, like think about it when you're doing it. Instead of writing it, like if I saw someone write this, it's like, yeah, this is correct, but look how complicated this looks. Like, and it's needlessly complicated, because 6 times 1 is 6. Just write 6. Like, think about it while you're doing it, instead of doing it mindlessly. Even if it was a 2, it would be helpful to just do the multiplication in your head and write 12, instead of having something that looks so terrible. Like, one of the reasons why you're having so much trouble with mental math is because you're doing stupid stuff.
Are you recording?
Yes. Okay, so 2 minus 1 is 1, so that's 6 times 1 is 6, plus 6 times 5 is 30, so it's 36. Okay, so the slope at 1 is 36 there, so it'd be very steep. Okay, so try to just do things a little bit smarter is what I'm saying. Instead of taking some you're supposed to. So you're supposed to look at the graphs. So if you graph sine x, everyone should be kind of familiar with how sine x looks. It looks like a wave that's going through 0. It looks just like that. And then you graph the derivative of it, and the derivative here in blue looks more like cosine, which I'm doing a terrible job at drawing. But you know what I mean. So we have sine and cosine, so it would have a maximum here. It would go through the 0 there. It would have a minimum there and a maximum there. It would look more like this if it's done correctly, theoretically. Okay, so you're supposed to notice things like that we have a maximum we have a 0 rather at our maximum. So our derivative has a 0 where our original graph had a maximum, stuff like that, where the original graph, the red graph, is increasing, the blue graph is positive, where the red graph is decreasing, the blue graph is negative, and the blue graph there is cosine. So if y is sine x, y prime is cosine x. Okay, that's what you're supposed to notice there. Okay, now for cosine x, doesn't quite work the same. So for cosine x, if I graph cosine x here in red, okay, so I have my max. Okay, the blue graph that would go along with that, we would have the 0 be here. Okay, but the thing is it would have to be, because on this side it's decreasing. Like here, it's going down. So our blue graph will certainly have to be negative. So that's not sine, because sine doesn't look like that. It's negative sine. So if y is cosine, y prime is not sine, it's negative sine. Okay, just because of the way that cosine is increasing and decreasing. Okay, so once you get to question, 5, that's asking you about cosine. When you get all the way down to the end there, that's supposed to be the realization. Okay, so the derivative of cosine is negative sine. Okay, so those are two that you need to definitely have memorized. Okay, so that the derivative of sine x is cosine x, and the derivative of cosine x is negative sine x. So we're just going to do a here, because we've learned how to do product rule before. We learned it yesterday. So if you have something like this one, y equals x squared sine x, what I see a ton of people do is they forget that the product rule exists, and they're like, oh, it's 2x cos x. And they're just they walk away from it, and they're quite happy. But that's not how it works, because when you have a multiplication and you're doing a derivative, you have to do the product rule. So here, on something like this, x squared is f, and sine x is g. So we have to do f prime g plus g prime f. So people get it wrong a lot because they just take the derivative of both. So you're not allowed to do that. So here, y prime will be the derivative of f, which is 2x sine x, because that's g, plus, and it's g prime f, so g prime is cos x, and f is just x squared. Okay, and I would write it like that. I would put the x squared before the cosine x, so it's clear that it's not part of the cosine x, and that's everything. You can't do anything else with this. Okay, so it's just a matter of writing out the rule. So doing f prime g plus g prime f, and just writing it out. Okay, is that easy enough? It's pretty straightforward, but you need to know your trig in order to do them. We're gonna learn the quotient rule right away, so we'll be able to come back and do b. But it's fairly. Okay, so here are the other trig identities. You need to memorize them. I'm sure people love that. cosine and sine come up a lot. Tangent comes up pretty often as well. So definitely memorize this, that the derivative of tan x is secant squared. I would say this one comes up sometimes, and that these two very infrequently come up. So they're listed kind of in order of importance. I would definitely know sine, cosine, tan. Like for sure, I would have those memorized. You should have them memorized after we're done the unit anyway, just from using them enough. Secant, again, gets used pretty often. It's kind of easy to remember. I don't know. I find it easy to remember because it's just secant tan x. Like, I don't know. It seems pretty easy. But cotangent and cosecant, to be honest with you, I don't have them memorized. And they pretty much never show up on a test or on an exam. So it's like you don't really have to worry about it too much. Okay? But you should know definitely cosine, sine, and tangent. Okay? Like, definitely. Okay, so let's look at the quotient rule. So same thing with derivatives of divisions. You can't just do the top and then do the bottom and divide them. You're not allowed to do that. It'd be nice if you could. Here, in this case, right, if we have h of x is f of x divided by g of x, so h of x is x6 divided by x3. Okay, the easiest way to do that would be, of course, to turn that into x3 and then take the derivative of that is 3x squared. Okay, that would be the easiest way to do that one, and it's definitely how I would do it. Okay, so that's just dividing them first and then writing the derivative. Now I will show you the quotient rule. So the quotient rule is that if you have the derivative of f divided by g, it's f prime g minus g prime f all over g squared. Okay? So it's not as easy as the product rule. Yeah, this slide is... I don't know what slide it is. It's right after the product rule, so wherever we were yesterday. Jumping around. What number is it?
47.
47. Okay, so this rule is not as easy as the product rule, unfortunately, but let's try it with this one. So if we had x6 over x3, and we're trying to take the derivative of that using this rule, I would do f prime, so the derivative of the top, which is 6x to the power of 5, times g, which is just the bottom, so x cubed, minus g prime, which is 3x squared, times just f, which is x to the power of 6, all over g squared. G is x to the power of 3, so it's x to the power of 3 squared. Okay, obviously in this case, this would be like kind of needlessly hard. You would not do it this way. You would just do the division first. But if we do this, we do end up with 6x to the power of 8 minus 3x to the power of 8 over x to the power of 6. Okay, so that's the same thing as 3x to the power of 8 over x to the power of 6, which is 3x squared. Okay, so it's the same thing. Okay, it does work. If you can do the division, obviously doing the division is easier. Okay, however, it's pretty rare that you can actually do a division with two polynomials. They'd have to be something like this, where it just happens to simplify very easily. Usually when you're dividing, there's no way to do it without using the quotient rule. So the quotient rule is pretty important, and you do need to have it memorized. So f prime g minus g prime f over g squared. Just the same as the product rule, but with a minus and then over g squared. Okay, so if you know one of them, you should memorize the other. Okay, so let's try it a couple times. Okay, so like 3z plus 9 over z minus 2, or 2 minus z, you definitely couldn't divide that, right? Like 3z plus 9 does not divide by 2 minus z, so you'd have to use the product quotient rule. So when I'm doing that, I would do the derivative of the top. So what's the derivative of the top? 3 times the bottom, which is 2 minus z, minus the derivative of the bottom. What's the derivative of the bottom there? Negative 1 times the top, which is 3z plus 9, all over the bottom squared. So 2 minus z squared. And z is not an ideal thing for me to be working with, to be honest. But I'll put a little line through it. Okay? So we have 3 times 2 minus z. I can expand that pretty easily. That's 6 minus 3z. Then I have positive 3z, positive 9, over 2 minus z squared. And I'm sure somebody in the room would make a bad decision and expand the bottom. Probably Aiden, if nobody else. Don't do that. Like, just leave it how it is. The only time you would do that squared is if it was something like x squared squared. Turn it to x to the power of 4. Or 5 squared. Turn it to 25. But, like, don't expand something like that. Now, on the top here, I have these cancel. And I have 15 over 2 minus z squared. It's pretty nice, actually. Worked pretty easily, right? That wasn't so bad. That was great. This next one's going to suck, though. Okay?
How do you know when to stop?
When you get to the end. Like, what do you mean? What would you do after this?
I don't know, but like, I look at something and I'll be like, what do I do after that? Like the first one, like the 6 minus 3, yeah, I would look at that and say like...
You wouldn't notice that you had two like terms that you could put together?
Yeah, no.
So look for like terms. You should be combining like terms, if it's possible. Okay, so this next one, yeah, I can tell it's going to suck because it has a radical in it. So I would write it out without the radical. So I'd write 4 times x to the half over x squared minus 2, like that. Okay, and then I would do it that way. So h prime here is going to be the derivative of the top. So I drop the half down, right? So it's 4 times a half. What's 4 times a half?
2.
2. So I have 2x to the power of what? Negative 1/2. Then I have the bottom, which is x squared minus 2. Okay, then I have the derivative of the bottom, so minus the derivative of the bottom, which is 2x, times the top, which is 4x to the 1/2. Okay, all over the bottom squared. Okay, now on top, what I saw yesterday, a ton of you guys are doing, and it's not ideal, but at least you were getting the right answer in the end, is a ton of you are expanding everything all the time and then trying to factor. If you just take if you stop at this step, once you write everything down, you should be able to factor immediately. Okay, so what I'm looking for, because a lot of you are having trouble seeing what you're looking for common factors. So here, what a factor is, because I think some of you don't know what a factor is, 2x to the negative 1/2 is a factor. Actually, there's more than one factor there. 2 is a factor, and x to the negative 1/2 is a factor. And x squared minus 2 is a factor. Okay, there's 3 factors in that term. Okay, then over here, there's 2, there's x, and there's 4x to the half. In fact, same thing with 4x to the half, I could split that into 4 and x to the half. A factor is something that's multiplying. So all those things are multiplying together. So technically in the second term there's 4 different things multiplying together. And I could combine some of them if I wanted to. Like I could rewrite that as 8x to the 3/2. It wouldn't make a difference, really. Okay, so it's up to you. So doing that is maybe fast, but definitely not expanding something like this. I would never expand something like that if it was me. Okay, so if you want to expand that second thing, or not expand, but if you want to simplify that second thing, you certainly can. So that's minus 8x to the 3/2. That is fair, I think, to write down. It's not really expanding, it's just simplifying things. But now, what's a common factor here are the x's. Okay, there's an x in each term, and you can just factor that x out right away. Like at this point, I can take out the x right away. I just look for the lowest exponent. So negative 1/2 is the lower exponent there. And also, I have 2 and 8, so I can pull out a 2. So I would pull out 2x to the negative 1/2, and I'd have a bracket. And then I'm asking myself, what do I have to times 2x to the negative 1/2 by to get this whole thing? Well, this part is already there. So I just need this part. So all I need is x squared minus 2. Okay?
You know, we need a 1 count or something.
A 1. Why?
Yeah, for 2x to the power of negative.
No, because if I multiply this by this,
Oh, it'd be just, okay,
I will get the entire thing.
I see.
Okay? This in the blue, what I have circled in the blue here, is one term.
Yeah.
Okay? So if I multiply 2x to the negative 1/2 by x squared minus 2, I will get 2x to the negative 1/2 times x squared minus 2. Okay, I'll get that. So I have it there right away. Then I think, what do I need to multiply 2x to the negative 1/2 by to get 8x to the 3/2? So it's going to be minus 4, obviously, to go from 2 to 8. And then x to the power of, and I'm thinking about it, what I'm thinking about here, because I have people asking me, what are you thinking? We have negative 1/2, and I want to get to 3/2. So that's a difference of 4/2, which is 2 whole. So you put 2 over x squared minus 2 squared. This is easier than expanding and then factoring. It just is. Like, you don't have to do that expansion. So you're pulling something out, and then right away, what you have inside the bracket there is significantly easier to factor or to deal with. You don't have to expand crazy stuff anymore. Okay, so I have 2x to the negative 1/2. And if I combine that stuff, I have x squared minus 4x squared, which is 3x squared, minus 2. Okay, over x squared minus 2 squared. Now there is one more thing here that you should do to truly simplify it and to have it look proper, and it's that you shouldn't have any negative exponents. So how can I get rid of the x to the power of the negative 1/2? Put it on the bottom. So I could have 2. And if you wanted to, you could pull out a negative here. These are both negative. It's kind of ugly. Like, you could put out the negative in the front and then have it be positive inside. That's not necessary, but it's just noticing, oh, those are both negative, so I could deal with it pretty easily. And you end up with that at the end. So as soon as you see a radical, you know it's going to be bad, basically. You're going to have to do some factoring, and you're going to have to simplify things out. So the reason that you need to know how to factor is because this is definitely the way that it would look on a multiple choice. Like, this is how your answer would look. So you need to be able to say that this first step way up here is equivalent to this step way down here. Now, without knowing how to factor, you're not going to be able to do that. You'll just be blindly guessing, basically, because they'll all kind of look the same, and you'll be like, who knows, maybe it's that one. And a lot of the time, things will end up canceling in these. It didn't in this one, but a lot of the time it does. So you need to kind of really be on the lookout and factor correctly. Okay, we're going to do this one, then I think we're going to start, actually, no, I'm going to do one more after that, and then we'll start practicing. But differentiate each of the following. So there's a choice that you have when you see something like this to use either the quotient law or the product law. So what you can do is you can change this to 4x to the negative 6 and do the product law, right? So you drop the negative 6, you get negative 24x to the negative 7, and you get negative 24 over x to the power of 7. That's how you would use the product law, or you can use the quotient law. If you use the quotient law here, you're like, the derivative of the top, what's the derivative of 4? 0. So you end up with 0 times x6 minus 6x5 times 4 over x6 squared, which then that's 0. So you get negative 24x5 over x12, which is negative 24 over x to the power of 7. So you get the same thing. Which is easier? The product rule. Generally speaking, the product rule is easier. If you have a quotient that's just one term divided by one term, do it as product instead. So how could I change something like this one to look more like a product? How can I write x to the power of 6 divided by 5 as a product instead? Yes, you would. So it's 1 over 5 x 6. Those are the same. Okay, multiplying by a fifth is the same as dividing by 5. So you just change it to that, and then it's really easy. It's just 6 over 5 x to the power of 5. Whereas doing quotient rule would have made this really quite ugly. Okay, does that make sense? Everyone okay with that? So if you see like divided by 3, just change it to multiplied by a third. Okay, or divided by 2, change it to multiplied by a half. Okay, it's pretty straightforward, but it's really important because I see people do like quotient rule with stuff like this, and it's like, I look at it and I'm like, God, what were they thinking? Because it takes like 3 times as long. So it's way easier if you just do it like this. Now the last one is a really typical type of problem. Okay, and it's a pretty easy one. We'll be looking at harder ones later. But it's when they tell you something like this, where they say like y equals uv, and let it be the product of the functions u and v. Find y prime of 2 if u of 2 is 3, u prime of 2 is negative 4, v of 2 is 1, and v prime of 2 is 2. People look at this stuff and they're like, oh my god, this looks terrible. But it's really not hard. It's just like, if y, so just be calm if you see stuff like this. If y is uv, then y prime is u prime v plus v prime u. Because that's the product law. Okay? Then it's just a matter of plugging the numbers in. So y prime of 2 is negative 4, because that's u prime, times 1, because that's v, plus 2, because that's v prime, times 3, because that's u. And then you just type it in, or do it in your head. So that's negative 4 plus 6 is 2. Okay? Like that. And that's all you do. Does anyone have any questions about that? It's pretty straightforward, but people do kind of panic when they see them.